Hey guys, so we're going to be doing some electrolysis problems. So let's start with the one up here. It says copper metal is purified by electrolysis. How much metal in grams could be produced from copper oxide by applying current of 10 amps at the appropriate negative potential for 12 hours? Okay, cool. So there's actually a way to do this the same every time. So you just have to know how the dimensional analysis is going to work. So this is how I do it. I like to put the grams of the substance. So in this case, whatever metal it is, metal in grams that's deposited. And then I like to turn that amount into moles, okay? And you'll see why I do that in a second. So anytime you want to turn from grams to moles, you need this proportion, right? So the grams that it takes for 1 mole. So I'm going to put 63.5 here. And then cool, now I have it in moles. We're imagining that we already have the amount, even though we don't, but we'll see in a second why. So 1 mole, we're going to find out how many moles it is. And 1 mole to be created will need a certain number of moles of electrons. Now, the mole of electrons in this problem is 2. And the reason we know this is because copper metal has an oxidation state of 0. It's a solid element by itself. But then when it's copper oxide, it's no longer that. And we can tell because of this nomenclature. This nomenclature tells us that copper is 2+ here. So between this, there's been a 2 electron transfer. In the solid state, it has 2 more electrons than it does in copper oxide. That's why it's 2 times, there's 2 more of a positive charge. My bad, not 2 times. So hopefully that makes sense. So each mole of electron, according to some calculations done by some other people, is 96,500 coulombs. So far we've done a pretty good setup. And when you do this setup, and this is the setup I'm going to use to solve for every single problem, what happens is the moles of electrons cancel out here, the moles cancel out here, and the grams cancel out here. So now we've just found how much charge is transferred, basically. So charge, this equation is very important, famous equation. Q equals, I guess it's IT, where I is current and T is time and Q is charge. But the thing is, Q, the charge, is actually the units for it are in coulombs. And current, the units for it are in amps, and time is just time, we know it. So that means if we only end up with coulombs here, we can put it equal to A times T, or amps times our time. So it said the current had 10 amps. So let's go ahead and put 10 in. And apparently it was running for 12 hours, so let's put that in too. So 10 times, and then we'll do a little small dimensional analysis here where we put hours. Where 1 hour is 60 minutes and 1 minute is 60 seconds. 1 minute is 60 seconds. And now we have it in seconds, which is what you need. It must be in seconds. And now we can solve for this like algebra. So even though, so just erase the lines so you can see what's going on. I'm gonna erase these lines real quick. Just draw like one line, like we would in an algebra problem. This times this times this over this times this should equal whatever this equals. So I am gonna do the calculations now. We should have 120 times 60 times 60. Yeah, so I did 10 times 12, that's 120 times 60 times 60. We're gonna get 432,000 here. Okay. 4, 3, 2, like that. Okay. And then what we're looking for, just keep that in mind and remember, is the copper metal in grams. So this is our X, this is our unknown. So what we have to do is isolate it. So now I'm going to take 63.5 and it's being divided here. So I'm going to multiply by 63.5 so we can get rid of it on this side. And I'm also going to multiply it here. So we'll get a bigger number here. Let's see what that is. Okay, it's a pretty big number. Let's write it down. So I got a really big number. Hope I did this right. Let's just write it down. 20,000. Cool. And then what we have to do is still isolate X, the amount of copper metal in grams. So we're going to divide by 2 and we're going to divide by 96,500 coulombs. So if any of this is a little confusing, then it might be worth it to do a little bit of an algebra review, find some Khan Academy videos or something. So 2, we're going to divide by both of these. So since we're dividing on one side, we have to divide on this side as well. So hopefully our huge number is going to get smaller and we're going to get something reasonable. So and we actually did, I just solved for this, and this here is equal to 142.13. So if we go here, we see that that is an answer. So eventually what we just did was isolate. So X equals 142.13 grams. And if you didn't get it the first time, it's okay. We're going to do more problems and then it should stick after a while. So let's move on to the next one. And in the next problem, we're going to use the same stencil that we were in the last one. X is just going to be in a different place. So I think that's what's confusing about these problems initially, is that every time it asks for something different. This time it says how long will it take? So this time it's asking for time. Some people like to change the dimension analysis, so they'll start this time with time. I don't like doing that because I don't think dimensional analysis is that easy for everybody. I like to keep it the same every time. So what I know works for me is having my grams here and then always having my grams per mole ratio here. So like that. And then I can always count on 1 mole being here, and then the moles of electron, that's just going to change based on your problem. These things are the things that are going to change by your problem, the things I'm leaving blank. But this 1 mole here and this 1 mole here should always be the same. Then another thing that's always going to be the same is that it takes 96,005. Oh, whoops. Sorry, my bad. I put that in the wrong place. 1 mole of electron is always going to be equal to, in charge, 96,500 coulombs. This is a constant, you just got to know. So now this shows how coulombs is going to be eventually just left by itself. And remember this equation, charge equals current times time, where this is C unit, the units are coulombs. This is amps per unit, and time, you know, time. So equals A times T. So this is the stencil. This is the stencil you always start with, and then you start filling it in. So here we say, how long would it take to electroplate a flute with 28.3 grams of silver at a constant current of 2 amps using AgNO3? Okay, so silver nitrate. So it already gave us the, it says we already know like the amount we want to plate. We just want to know how much it's going to take. So let's put the amount here, 28.3. Okay. And then here it gives us much needed information, the grams per mole. So 107 is what I'm going to put, or I'm going to round it to 108 because it's closer to 108 and I don't feel like dealing with decimals right now. So then let's go to the moles of electron. Let's see how much are transferred. Well, silver by itself has an oxidation state of 0 because it's an element by itself, and those always have oxidation states of 0. But silver nitrate, it's basically going to have an oxidation state that depends on what it's paired with. Nitrate is a polyatomic ion, and since it's a polyatomic ion, it's always going to have its own charge as its oxidation state. So since nitrate has a charge of -1, which is something you just have to know, like by memorization, silver is going to be +1. That's its oxidation state. So 1 mole of electron is transferred between its ionic state, and its silver metal by itself state. So this one's actually not that bad. Now we just need to put in the amps, 2 amps. And then this time our unknown is the time. So see how the stencil can be carried over from problem to problem, and you don't really have to keep too much track of things. So this is how I like to do it. Now we just need to basically isolate T, and it's going to be much easier this time because we can solve for all of this at once. So I'm just going to erase the lines just so you can visibly see that this is just a multiplication division problem. So that's how it works. This times this times this divided by that times this times this. So let's put this in the calculator, see what we get. Cool. So for this side, I got a pretty big number. Let me just put it in. Got 21,265. Cool. And this is coulombs, right? Because that's all that's going to be left over. Nice. And then we just need to know the time. So let's isolate the time by dividing by 2 on each side. New number I get is 10,632. Let's write that now. And this should be equal to our time in seconds. So seconds. But it doesn't want it in seconds, it wants it in minutes. So the last thing you have to do is convert that. So to convert that, we just have to divide by 60 because there's 60 seconds in 1 minute. And yeah, I get 177. Dang, that's not an answer. Wonder what we did wrong. Oh, I think this is because of the rounding, most likely, because I rounded this to 108, because we definitely did it correctly. So I'm guessing that the answer should be 211 because that's the closest to 177, which I got in my calculator. So hopefully when you guys do it, you get the right answer. Let me just check real quick to make sure that it is 211, 63, and we didn't make a major mistake. Yeah, so 63 is a 211. So I believe the reason I'm a little off is because when you round in these situations where you're dealing with huge numbers, rounding has a much greater effect. So I got 177, but if you're using your significant digits and using this number, you should get 211. Okay, so let's do another one, and this time I won't round, and we'll use the same stencil and everything. So this one says how many grams of aluminum. This one says how long it will take. This one says, this one's also about time. Okay, so let's do 64. How many grams of aluminum metal can be produced by electrolysis of aluminum oxide using a current of 100 amps for 24 hours? So let's set up the stencil. So this is the grams of our metal, which is deposited, and then it's always going to be converted to itself in moles. So 1 mole, and then the grams here, it's just dependent on the molecular weight. Okay, and then 1 mole, for every mole, there's a certain mole of electrons that must be used to do this process. So that's something that depends also on the problem. but 1 mole of electron is always going to be equal to 96,500 coulombs. So this is the stencil. Same thing we used above. And it's going to be equal to amp times time. And now it's our job to fill it in. So this is the stencil. So metal is what we're trying to find. This is what we're trying to figure out. So let's put in what we have. We have 26.982. 26.982 grams. Nice. Now moles of electrons. So aluminum by itself is going to be 0 oxidation state because it's a solid by itself. And then here we have aluminum oxide. So like metals, aluminum is not a group 1 or group 2 metal, so it doesn't really have a priority. What takes priority is going to be the oxygen here. Oxygen has an oxidation state of 2-. Since this is a neutral compound altogether, what we have to do is get this to have an oxidation state that balances the oxygen's oxidation state. So together we're going to have 3 times 2-, 6-. So aluminum must have a 3+ state in order for this to occur, since there's 2 of them and we want to balance it with a 6+. So hopefully that makes sense. If it doesn't, I think reviewing assigning oxidation states would be a good video for you. So 3 moles of electrons for this situation, and now we can do everything. We just need to basically plug in our amps and our time. So we had 100 amps, and then we have 24 hours. So 24 hours, and then we know 1 hour is 60 minutes and 1 minute is 60 seconds. Cool. So I'm going to solve for this side first, see what we get. Got big number, let's just put it down. Right. 8,640,000. Cool. Here's our number. And now we just got to solve for this side like an algebraic problem and isolate. So I'm gonna first multiply this. Since these are ones, I'm just gonna ignore them because they're not really going to cause anything different on the bottom. So we're just gonna do times 26.982 to get rid of this on the bottom and carry it over to the other side. So times 26.982. Okay, cool. And then let's do this again, multiply. Right, so now I get even bigger number. Let's write down what we get. Cool. So now everything's going to be isolating this guy, finding out the number of grams of aluminum. So like we said, we can ignore 1. It's not going to really do anything, but we can divide by whatever this equals. So 3 times 96, or I guess let's just divide like this. It'll be the same thing as solving first to see what it equals. We'll divide like this, get rid of it here, and then that means we gotta divide it here. And if you don't like the way I'm doing it, you can do it your own way. Like you can multiply 3 by 96,500, get a number here, and then deal with one number at a time. It's totally up to you, whatever you feel comfortable with. Okay, but let's just solve for it the way I'm doing it for now. So this stuff goes, and now this is isolated, which means whatever this equals should be equal to this, and there's not a lot of room for me to work with. So let's just see what it equals. Hopefully we get the right answer. So divided by 3 times 96,500. Cool. So I got 805, and that is indeed an answer, 805 grams. So this is how you do these, guys. I could go on, but I think I'll leave the rest for you guys. And hopefully this video was helpful. Good luck on your test tomorrow. See you guys soon. All right, bye.